To finish up here, last part of chapter 8, we had just a couple more examples to do. We've been talking about empirical formulas and molecular formulas and how to calculate both of those. So remember, when we have the empirical formula, there's several steps that we have to follow to calculate that. And it does help us calculate the molecular formula. So to calculate the molecular formula, again, there's really sort of three things that you need to calculate that molecular formula. The first thing is obviously the empirical formula. So either that would be given to you or you may have to calculate it. In most cases, you're probably going to need to calculate it. And we do calculate it again by converting everything into grams. And then the first thing we would want to do after that is convert grams into moles. We would use the molar mass from the periodic table to do so. Once we have it, everybody in moles, all the elements in moles, we want to divide by the smallest number of moles. And we're going to take the smallest number of moles for whichever element that is and basically divide it by everybody else. If we get all whole numbers after we divide by the smallest number of moles, that frankly is going to give us our empirical formula. So it would be our empirical formula if we got all whole numbers are really, really close to whole numbers, like 1.99 is close enough to 2, and so forth. You don't want to go a little bit above it or a little bit below it. But remember that if it's a little too far from the number, we cannot just round. So for like a 1.5 B2, for example, that 1.5 is too far to round. So we cannot round it to the next whole number. We do need to figure out a number to multiply it by to get to a whole number. In this case, we could actually multiply it by 2 to do that. And that would give us the proper empirical form of A3B4 in this case. Once we have the empirical formula, that again is the first thing that we really need for the molecular formula. We need to get the empirical formula's molar mass. So we go to the periodic table, we add up all the parts of the empirical formula, and that gives us our molar mass of our empirical formula. The third thing that we need, which is commonly given to you in these type of problems, is the approximate molar mass of a compound. So somewhere in there, they will say that the approximate molar mass of the compound is this many grams per mole, or the compound ranges from this many grams per mole to this much grams per mole. It may even be a range, but that's usually given to you. And what we want to do is after we have the molar mass of the compound, which is given to us, we have the empirical formula's molar mass. What we really want to do is divide those numbers. So we would take the molar mass of the compound, and we would divide that by the molar mass of the empirical formula. When we do that, that is going to give us a number, and that number is what we're going to multiply the empirical formula by. It's basically a factor to multiply the empirical formula by. So, for example, if we look at my empirical formula that I got there before, which was A3B4, and let's say that we did this calculation where we took the molar mass of the compound and divided it by the molar mass of the empirical formula. And let's just say, for example, again, just making up this number, we got a 4. I would then multiply the empirical formula by 4. All the elements by 4, the subscript basically. And that would give me our molecular formula of A12B16. So in our example here, our empirical formula A3B4 and multiplying by that factor gives us A12B16 as our molecular formula. All right, so now that we talked a little bit about it, let's actually look at a problem here. This is one from your notes. What is the molecular formula of a compound that's composed of 1.52 grams of nitrogen, 3.47 grams of oxygen, and has a molar mass between 90 and 95 grams? It's really 90 and 95 grams per mole. We're looking for the molecular formula and the molar mass of the compound to four significant figures. In this particular case, we're giving a range for the approximate molar mass of the compound. Anywhere between 90 to 95 grams per mole is our approximate molar mass of this compound. After we're done with the calculation, we'll be able to actually figure out what the correct molecular formula is, and the correct molar mass for it, which is sometimes referred to as molecular mass. So a reminder again, to calculate the molecular formula, we need the empirical formula, which in this case we do not have, so we're going to have to calculate it. We need the molar mass of the empirical formula, which we also will have to calculate. And the third thing, the molar mass of the compound, which, as I circled there to the left, we already have in this case. So we got one of the three things we need to calculate the molecular formula. So the first thing we're going to do after I kind of fix my writing here, I think I went off the screen. So give me a second here, grab an eraser, maybe do a little bit of erasing here. There we go. Kind of put it all on the screen. It was close. It just fell off there at the end. 90 to 95 grams per mole is our approximate molar mass. All right, so turning back to the empirical formula here, we're going to calculate it by first taking our grams of each of these elements, which were given to us, 1.52 grams of nitrogen. Using the molar mass from the periodic table, 14.01, we're going to convert that into moles. We're going to do the same thing here for oxygen. We have 3.47 grams of oxygen using the molar mass from the periodic table, which is 16 grams per mole. We will also obviously convert that into moles. So it looks like here, grab my calculator, we got a 1.52 divided by 1401, going to give us a number of 0.10849 moles of nitrogen. Also now dividing the oxygen, 3.47 divided by 16, going to get us 0.2168 moles of oxygen. In this case, we're now ready to divide by the smallest number of moles. And looking at it, it is the nitrogen that we want to divide by. So we're going to divide everybody here by the moles of nitrogen, 0.10849, and divide the oxygen by 0.10849. Actually, 99, I'm sorry, it looks like. We're going to get 1 there. And we're going to divide the other guy there. And we will end up with a 2, I believe. And that's going to be pretty much 1.999, which again is close enough to round here to 2. And I think I misspoke. It is 0.10849 we're dividing by. So because we really hit whole numbers here for both of them, and again, that 1.999 close enough to round, gives us an empirical formula for this compound of 1 nitrogen and 2 oxygens, are basically NO2 being our empirical formula. Now that we do have the empirical formula, what we want to do is the second thing that we need after we check that off our list is we need the molar mass here of the empirical formula. So we're going to go back to the periodic table. We're going to calculate our molar mass. So that's 1401 grams per mole for our nitrogen. That's going to be added to 2 times 16 grams per mole for each oxygen that's present. Going to give us a molar mass of this compound of, looks like 4601 grams per mole. And we can now check that off our list. We now have the molar mass of the empirical formula. We were given the molar mass of the compound in the problem. Again, in this case, it is a range, so you can choose anywhere in that range. So if you want to kind of go halfway between the two numbers, we could start doing it that way if you like. We could divide by 92.5 grams per mole. And again, that's right there kind of in the middle of the range in terms of the molar mass of the compound. So we take our 92.5 grams and divide it by the molar mass of the empirical formula, which is 4601 grams per mole. We will get basically a factor to multiply our empirical formula by of approximately, in this case, 2. It's 2.01. That obviously is close enough to round to 2. Now, let's say you didn't want to choose sort of halfway in the middle, but you want to maybe take the low end of the range. And the low end of the range would be 90 in this case. And you could do the same thing, take 90 grams per mole, divided by 4601 grams per mole, going to give us a factor to multiply the empirical formula above 1.96. Once again, close enough to round in this case to also give us a factor of 2. You could also have chose the higher end of the range here. And if you chose that higher end of the range, you're looking at really 95 grams per mole. So let's just do it here while we got a little bit of space. So we'll squeeze it in here. 95 grams per mole divided by 4601 grams per mole also gets us a factor of 2. I think here 2.06, which once again is close enough to round it to. So you can see that regardless of where you chose, middle range of the molar mass, low end of the molar mass, or high end of the molar mass, we basically got the same factor. So when you have a range like this for the approximate molar mass of the compound, you could really just kind of choose any number in that range, do a little bit of rounding to the nearest whole number, you get the proper factor. So now that we do know that it is 2, we need to multiply the empirical formula by. That will give us our molecular formula, which is N2O4 in this case. So our empirical formula being NO2, our molecular formula being N2O4. And now that we obviously have the molecular formula, we can calculate the actual molecular mass or molar mass of this compound for N2O4. Again, we're going to the periodic table here. 2 times 1401 grams per mole for our nitrogen. 4 times 16 grams per mole for our oxygen. Going to give us a molar mass of our molecular formula of, let's see here, grabbing the calculator, punching it in, and we get something like 9202 grams per mole, which is 4 significant figures, which is what the problem looked for. So once again, you could calculate the empirical formula first. In this case, we then got the molar mass of the empirical formula, which is the second thing that you need. And the third thing is usually given to you, which is the molar mass of the compound. And obviously using that, we got our factor of 2 to multiply our empirical formula by. All right, let's take a look at one more example, which I think should be your last example. And in this case, we got phosphorus oxide contains 43.64% phosphorus, 56.36% oxygen, and has a approximate molar mass there, 283.89 grams per mole. We want both the empirical formula and the molecular formula here. So remember that when you are given something in percentages in terms of the elements, percent composition by mass is really what that is. You want to just kind of quickly look at both percentages and make sure that they do add up to about 100%, which they do in this case. Again, if they don't, you're kind of missing something. You're missing one of the elements if you don't have that. Because they do add up to 100%, we can assume that we have 100 grams of the substance. What that does is basically turn our percentages into the same number of grams. So in this example here, we would have 43.64 grams of phosphorus instead of percent, and we would have 56.36 grams of oxygen, once again, instead of percent. Once again, we're going to convert these grams now into moles using the molar mass from the periodic table. Going there and looking up phosphorus, looks like a 3097, I believe. So we're going to use 3097 grams per mole to convert our phosphorus into moles. Using the molar mass of oxygen, which we've used previously, is 16 grams per mole, I think, still. Good thing it hasn't changed. All right, so now we got our moles of each of these guys. We're going to take 4364 divided by 3097, going to give us a number here for our moles of 1.4091 moles of phosphorus. Taking our grams of oxygen, which is 56.36, and divided by 16, going to give us our 3.5225 moles of oxygen. Here, phosphorus is our smallest number of moles, so we're going to divide everybody here by the moles of phosphorus, which is 1.4091. That obviously is going to give us a 1 for phosphorus. When we divide out the oxygen, 3.5225 divided by that 1.4021, we get 2.4998, which is approximately 2.5. So if we were to write our empirical formula at this point, we would have PO 2.5. And as we've talked about before, that 2.5 is not good, too far to round. So once again, we need to find a factor to multiply that by. So 2.5 times 1 is 2.5. 2.5 times 2 is 5. So the factor, though, that we want to multiply by is actually the 2, not the 5. So that's a common mistake. And we want to make sure we multiply everybody in that formula by 2. That gives us our proper empirical formula of P2O5. Again, a very common mistake is to multiply by the result and not the factor. So again, multiply by 2 here. Now that we have the empirical formula, we can check that off our list. We're going to now get the molar mass of our empirical formula. And to do that, we'll go to the periodic table. We got 2 times 3097 for our phosphorus. We also have 5 times 16 for our oxygen there. And that's going to give us a molar mass for our empirical formula here of, punch that in there, grab the calculator, probably helps. All right, let's see here. 141.94 grams per mole. So now we really have 2 of the 3 things we need for the molecular formula. And the third thing is again found in the actual problem, the approximate molar mass. So we're going to take the approximate molar mass of the compound, which in this case is 283.89. We're going to divide it by the empirical formula's molar mass, which is 141.94. And that's going to give us our factor to multiply the empirical formula by. And it looks like when you do that, that's going to give us a factor of approximately 2. So we're going to take our empirical formula and multiply it by 2. To give us a molecular formula in this case, P4O10. So here in this case, we have our empirical formula we calculated first. Then we got our molecular formula by using that factor once again. It's a very common thing that you'll need to do is usually you'll need to really calculate the empirical formula through the process and the steps that we did. Convert grams to moles, divide by the smallest number of moles, get the molar mass of the empirical formula, and then get the molecular formula calculated after that. It's a very common process that you do usually need to do is to calculate that empirical formula first. So you can then get that factor to multiply the molecular, the empirical formula by to get to the molecular formula. All right, well, I think that wraps up the last couple of examples that we had for Chapter 8. So I hope this was helpful. I'll see you on the next one. Have a good one. Bye-bye.